Hello students, discuss some more aspects of mathematical physics today. So we'll first start with small oscillations. Now, small oscillations are characterized by those oscillations where the force acting on the particle is zero. A particle at such a point with zero velocity will be at rest, and the force when also the force acting on the particle it vanishes, then the particle is also said to be in equilibrium. Now this equilibrium has two different types. One is called a stable equilibrium and another one is called an unstable equilibrium. Stable equilibrium is where the change in potential is positive at neighboring point, near point. So it means that the potential is minimum at that particular point. So you can say that P is a minimum. So any change will cause a positive change. The potential will rise up if there is any change occurring. However, in the case of an unstable equilibrium, it is just the opposite. It is negative. So it's obvious that this P is max at that point where the equilibrium is present, and also this is also equal to the total energy, since potential energy is maximum. So there is no kinetic energy involved in it, and that is equal to total energy. So these two are different types of equilibrium. Now, while discussing small oscillation, we need to understand a concept of normal coordinates. So normal coordinates are the generalized coordinates where each of the coordinates is oscillating at the same frequency, which are then they are called the normal coordinates. Okay, now so based upon the small oscillations we'll discuss some systems with degrees of freedom, and what are the normal frequencies involved in these systems. So first we'll take about a parallel pendulum. Parallel pendulum is that pendulum, so we know that this is the normal pendulum. Now if this normal pendulum is attached with another bob and a spring constant K, then this becomes a parallel pendulum. So this will oscillate on its own, and it will also be related to this another mass. So in this case it will have L omega L theta, whatever this K, and this is M1, this is M2. Say others are same, so M and M. So in this case the normal frequency will be G by L plus 2K by M. This is the normal frequency, and so this goes for parallel pendulum. Secondly, there is another thing called a double pendulum. So double pendulum is also a modified form of the single pendulum. So if we have two bobs attached with each other, so the only difference is there is no spring constant, so there are two masses, A1 and A2. So in this case the frequency of oscillation, the normal frequency, is mass independent. It's quite interesting. So here the frequency oscillations omega will be simply, let's say, omega square would be G by L 2 plus root 2, or we call it as omega plus square. There is another frequency omega minus square G by L 2 minus root 2. The two normal modes of frequency. This goes for the double pendulum. We have another system called triple pendulum. So here again the number of bobs increase. Previously it was 2, now it will be 3. 3 masses attached to each other. So well, in this case you will have 3 modes of oscillations, 3 frequencies of oscillations. Like we have omega 1 as G by L plus 2k by m. Then we'll have omega 2 as being G by L plus 2k by m if the masses are same, and omega 3 will be equal to G by L minus k by m. So as you can see, the first two are equal. So it effectively has 2 identical frequencies. So there are 2 modes of oscillations. One is this one, omega G by L plus 2k by n, and another one is G by L minus k by m. So this is one of the cases. And some of the practical cases. What about the linear triatomic molecule? We know that the molecule is not fixed, it is always in vibration. So if we have a linear triatomic molecule, what will be the modes of frequencies in it? So let's say there are 3 atoms attached linearly, and the middle one has got say mass capital M, and the masses at the 2 ends are small m. So in this case, the frequency, there will be only 3 frequencies. One is omega 1 will be equal to 0. Now this frequency, it actually indicates translatory motion. Translations involved in it, and it is not associated with oscillations, and those which are associated with oscillations are omega 2, which is, you can say, is the normal k by m, and omega 3 is equal to k by m in the bracket 1 by 2 small m by capital M. So these are 3 frequencies involved in a linear triatomic molecule. Now, for this linear triatomic molecule, there will be 3 degrees of freedom for rigid translations and rigid rotation, and account for only 2 degrees of freedom. So if it is a rigid translation, then it will have 3 degrees of freedom. So it is 4. So talking about the linear triatomic molecule. So if it is a rigid translation, by what rigid means, the atoms are the atoms are fixed. In this case, there will be 3 degrees of freedom in x, y, and z directions, and if it is a rigid rotation, then it will correspond to 2 degrees of freedom. And there will be 4 modes of vibration. We talk about vibration, and then it will correspond, there will be 4 modes. And out of these 4 modes, 2 modes will be the longitudinal vibrations, and the 2 modes will be transverse vibration. That's quite obvious. If you look closely, say there are, as we have said, there are 3 atoms. This is capital M, this is small m, this is small m. Let's see about vibrations first. Now, as you know that these atoms will keep on vibrating. So one vibration will be, say, along the bond axis. Okay, so keep on vibrations. So, and one, so the atoms will squeeze here and squeeze here, and then expand, squeeze and expand. So this is along the bond axis. So this corresponds to this longitudinal vibration. So there are 2 modes, either it is squeezing and it is expanding, considering these 2 masses. And also the same thing can happen if we consider the transmode mode. So this atom can go up, while vibrations, if we consider vibrations, this atom can go up, these 2 atoms, and this can come down, or it can go in another fashion. So also there are 2 translational vibrations associated with them, and so that counts for these 4 modes of vibrations in the case of linear characteristic molecule. So we will now change the topic, and we will go to something else. We will not fix ourselves to any particular topic, and we will try to be little comprehensive regarding the subjects, and we will also repeat some of the concepts as often required. So from small oscillations, now we move on to something called Lorentz condition for gauge invariance. Actually this is electrodynamics. So now that we know that there is those who have a little bit idea of electrodynamics, they already know that in electrodynamics we have a vector potential and we have a scalar potential. Now you can represent the vector and the scalar potential in an equation in the following form. We can write that del dot A plus mu epsilon del phi by del t is equal to 0, and B is equal to del cross A E is equal to, E minus del A by del T is equal to minus del phi. Now this expression is what is the Lorentz gauge. Now it is based upon the concept that the Lorentz force Fl acting on a charged particle in an electromagnetic field can be written in terms of the two potentials. The Lorentz force acting on a particle, obviously charged particle, in an electromagnetic field. Now, we know that whenever a charged particle enters and say an electric field, so it will have this force QE, the electric field, and if it is having a velocity v, then and if it enters a magnetic field, then the force acting on it to the magnetic field will be V cross B. So considering those, the total Lorentz force Q into V cross B actually. Total Lorentz force is Q E plus V cross B. Now, how to write this force in terms of the scalar potentials and the vector potentials, that is in terms of A and phi. So in that case, we can write Fl as equal to, is equal to this charge remains the same. Let's put it as Q, and it will be minus E into phi minus V by C dot A minus 1 by C del A by del T. This is how you can represent Fl in terms of the scalar potential phi and the vector potential A. And this operator, this d by dt, is actually del by del t plus mu dot A, V dot A plus T dot A, and it's mobile operator. So this is how you present. This is actually the Lorentz gauge, and as we have saved, E minus this is the Lorentz gauge, and from here we actually find out the Lorentz force. Now, from electrodynamics, we again move to something called through quantum mechanics, and we will discuss about the theory of scattering. Now you know that in scattering, if there is a wave function psi at which goes to infinity, so it can be expressed as equal to e to the power I k dot r plus f theta, because f theta is colored one, plus f theta e to the power I k r by r, where this is the incident wave, and this is the scattered wave. And f theta is the scattering amplitude. It defines how much scattering has taken place. So from the scattering amplitude, we can actually find out the scattering cross section. Sigma theta, and it is simply the mod of this theta, or the square of the scattering amplitude, so scattering cross section. So this is so to find out total scattering and cross section for the say spherically symmetric potential. So there is a spherically symmetric potential. It means we will be dealing with the spherical polar coordinates r, theta, and phi, and we need to find out the total scattering cross section. Total scattering cross section. So this again is integrate the cross section obtained from the scattering amplitude, so it will be 2 pi 0 to infinity sigma theta sin theta d theta, the total scattering cross section. Now, according to Born approximation, the scattering cross section in terms of theta and phi is equal to minus 2 mu by h cross square into integration the potential VR into e to the power I k r dr, and a little fresh d f theta phi is equal to minus 2 mu by h cross square integration VR e to the power I k dot r dr. Now the potential is spherically symmetric. This potential that we talk about. So potential is spherically symmetric. So the amplitude wave function, the scattering amplitude will mainly depend upon theta, and it will not be dependent upon this phi. So we can simply write f theta as equal to minus 1 by k integration 0 to infinity r sine kr vr dr. So we can see that there is a slight point over here. So instead of written about ikr, we have now written r sine kr, and the constant that the outstep integration is also changed. So it is minus 1 by k, where k here is the propagation constant, and it has the value capital K. Here we have used capital K. This is not small k. This is not the k that we. This is actually the propagation constant, but we have used a capital K. So this capital K is related to the small k as 2k small k sine theta by 2, where this k is the propagation constant, not the capital one. So using this value of the scattering amplitude, we can actually again derive the differential scattering cross section that we have initially found out to be sigma theta as equal to mod of f theta whole square, and so this happens to be equal to minus 1 by k 0 to infinity r sine kr vr dr whole square. And so now, okay, well, this is based upon the Bond's approximation, and there is actually a condition for validity of Bond's approximation. So condition for validity of the Bond approximation and that condition is 1 by mod of 1 by 4 pi 0 to infinity e to the power I k r minus r dash divided by r minus r dash v r dash into e to the power I k dot r into dr dash. this should be much less than 1. So this is the condition for the validity of Braun's approximation. Okay, so the next topic that we will take up in the mathematical physics section is motion under central force. Now, what is actually a central force? Central force is that force, say, which is actually a function of the distance from a point. So, if you would like to find a central function of r, where r is this distance, this is actually the central force. Distance from the center defines that force. Now, the force between two interacting particles is primarily central force. So, force between two interacting particles is primarily the central force. Now there are two main features of central force. First is conservation of energy. And the second is conservation of angular momentum. There are two main features. And also for the central force, the orbit, say this is the particle which is being acted by a central force at the center, and it moves around an orbit. So this orbit, it lies in a plane where which is perpendicular to the fixed direction of angular momentum. So it is in a plane which is perpendicular to the fixed direction of the angular momentum. This is another feature of the central force. And the total energy of the system in the central force is half m r naught square. This is for the kinetic energy, plus L square divided by 2mr square plus Vr is equal to a constant. So there are three terms. One is the kinetic energy. This is the energy involved in the angular momentum, and this is the potential energy. So both of them add up, and they are implicit as a constant. Then this is actually the total energy of the central force, and the equation of the path or orbit. Equation of the path or say the orbit, it is given as del square u by del theta square is equal to minus u minus m divided by L square u square function of 1 by u, and u is actually the inverse of the coordinate. So the equivalent one-dimensional problem will be the energy is equal to V dash plus half m r square r dot square, and the potential V dash will be equal to minus T by R plus L square divided by 2m r square. So this is the equivalent in one dimension energy, total energy and potential energy. If we plot the equivalent, one-dimensional potential that we just derived, and we do it for an attractive potential. Now the plot will look like. So let us once again write the equivalent one-dimensional equations. So they are E is equal to V dash plus half m r dot square, and V dash is equal to minus K by R plus L square plus 2m r square. So if you plot V versus V dash, minus K by R, so we'll obtain a plot like this. So this will be for E1. This will be for E2, E3. This will be again for E2, and this will be again for E1. And if we plot V dash with respect to R, so it will show a plot like this. And this will correspond to the E, and this one will corresponding to R dash. R1 and R2, say there are 2 points, one is R1 and one is, say, R2. So this plot is for a one-dimensional potential for an attractive inverse square. Attractive inverse square law. Reciprocal square Kepler's law. Now for a restoring force, if somebody talks about the for one-dimensional potential, for a linear restoring force, I think here this will be talking about an harmonic oscillator. Then the plot of V dash versus R will look like following this, and this will correspond to E. Sorry. This will correspond to L is equal to 0, and this is how the E will look like. It's the E. So for the inverse square law, there is a real theorem. Okay. And it says that T, total kinetic energy, is equal to minus half summation F dot R dot and for inverse square law, twice of T plus V is equal to 0. Now we know that when an orbit is moving under centered force, it mainly moves in elliptical orbits. Now, what parameters actually govern this elliptical orbit? The elliptical orbit is governed by a parameter called eccentricity, or E. So, what is that parameter eccentricity? Now, for look into the features of an elliptical orbit. First one is the energy E is equal to minus K. It's a different color here. E is equal to minus K by 2A. So A is actually the major axis of the elliptical orbit. This is actually the major axis. This is 2A, and this is the major axis of this elliptical orbit. So it means that all the ellipses with the same major axis will have the same energy. second feature of elliptical orbit is the Kepler's law. That means the time period square of the time period of evolution is proportional to the cube of the cylindrical axis. So the period of elliptical oscillation, that is the tau square of that, is proportional to the cylindrical axis cube. These are the two main features. Now, for the condition of a stable orbit, is when the potential energy, the simple square, del square V by del R square at a particular point at R is equal to 0 is greater than 0. This is where this is the condition of the stable orbit. So according to Kepler's law, as we have told, that we will have a parameter called eccentricity, and it will define the orbit of the particle, whether it will be elliptical or something else. Now, this eccentricity is equal to 1 plus 2e L square divided by mk square. This is the value of eccentricity. Now, if the eccentricity value, E value, is greater than 1, and also energy associated with the particle is more than 0, then the path of the particle will be a hyperbola. The first case. The second case is when eccentricity is equal to 1 and the value of E is also equal to 0. So there is no energy involved in the orbital motion, also eccentricity is 1. So this will make the orbit as a parabola. The third is one when E is less than 1 and also the energy is less than 0, then we will get the elliptical orbit, ellipse. And if E is equal to 0 and capital E is equal to minus mk square by 2l square, so it means that the shape of the orbit will be a circle. So we can say that it is only this condition, when satisfied, only then the shape of the orbit will be elliptical one, otherwise we will have different types of orbits. Now, from this classical mechanics we again move on to electrodynamics, and let us move on again to the scalar and vector potential. As we have discussed that we can express the Lorentz force in terms of scalar and vector potential, and we have also discussed about the Lorentz gauge. Now, how to if the electromagnetic potential, how to express them in terms of uniform electric and magnetic field. So it's the EM potentials. In uniform electric and magnetic fields. So the first one is your scalar potential phi, and it is equal to minus E dot R, and then the scalar potential E as equal to 1 by 2 B cross R. Now we have discussed about the Lorentz gauge. There is another gauge which is called Coulomb gauge. And this is Coulomb gauge. Wherein it restricts the divergence of A as divergence A is equal to 0. And also according to this gauge, the potential, the scalar potential phi can be expressed in terms of 1 by 4 pi epsilon integration V rho density divided by any change in position. This is the charge density. That's it. We'll take up in our next class for the features of mathematical physics.